This brief instructional video is designed to introduce the idea of invariance. It's the concept that we can have something and represent it multiple ways mathematically. As long as the mathematics all works out, the physical behavior should be the same. Everything we predict under the first representation should be mirrored under the second representation. And the advantage of understanding an idea like invariance is that it allows you to spend more time and mental energy focusing on what the underlying mathematics is telling you about the physics and chemistry, and less time worrying about doing a whole bunch of math. It's great if you're a math person, but if you're into it for the chemistry, like I am, then you're going to want this idea. So a prime example of this would be for the wave function for the one-dimensional particle in a box. So we take this wave function, we have some normalization factor, and what we use is sine n pi x over L. Sine wave is guaranteed to be 0 when x equals 0, and with the argument n pi x over L, where n is an integer, at x equals L, you'll always have a value of 0. So it satisfies your standard boundary conditions for the one-dimensional particle in a box. Because it is a sine function, it will be an eigenfunction of the Hamiltonian. So when we take the second derivative, we'll be able to get our energy eigenvalues out and all that great stuff. And the sine wave is great in terms of conceptualizing what the individual energy levels look like. For each integer value of n, you're going to get the same number of half cycles of a sine wave. And so that's something that we're very familiar with. But the challenge rises in trying to do integrals. Unless you've memorized the entire integral table, doing integrals of sine waves is just really difficult to conceptualize immediately. But it turns out that we could use the idea of invariance to get a replacement wave function for this. And it requires use of the Euler identity. So if we take this, we have cosine kx plus I sine kx. And for the negative case, we have cosine kx minus I sine kx. Well, if we subtract these two equations, that eliminates the cosine and leaves us with just exponentials on one side and sines on the other. So we can have e to the I kx minus e to the negative I kx, and that will be equal to 2I sine kx. If we divide both sides by 2I, then what we've done is have on the left-hand side an expression that's written in just exponentials, and that equals sine of kx. So at this point we could write out a proposed wave function for the one-dimensional particle in a box using just exponentials, because we know that n pi x over L would replace the kx, and so we would do the same thing over here. And now we have the advantage of exponentials, which are easy to take derivatives of, easy to take integrals of, and that may give us something that's easier to work with mathematically. And as long as these two things are equal, we can expect to have the same behavior described by a wave function that's using exponentials as one that's using the sine wave. What's nice then is that we have something that we can represent in two different ways, and depending on how we're thinking about it or how we're looking at it, we can get the same physical behavior, but a possibly easier time of doing the mathematics. And that's why invariance and having the ability to move cleanly between different representations of a single concept is so important.